Today I wanted to talk about joint work with Antal Balog on the sum of dilations of a set. This work was done over 5 years ago and was actually when I was a master's student at University of Wyoming. Right now I'm currently a PhD student at University of Illinois at Urbana-Champaign. We have a pretty short abstract, and if you're seeing the result for the first time, you can just think P is equal to 1. So in that case we show that A plus QA is at least Q plus 1 times the size of A minus a fixed constant only dependent on Q. It turns out that this is best possible, up to the additive constant, as it can be seen by taking A to be an arithmetic progression. And equation 1 is telling us that the arithmetic progression shows that our result is nearly optimal. Before I talk about what we did in this paper, let me mention some of the history of the problem. So the main result in the area was due to Boris Buch, who proved a nearly optimal lower bound for the sum of K dilates. You see that there's that little o of A term, and so the goal of our paper is to turn that little o(a) into a constant. In our paper we only consider the case of 2 dilates, but I continued to work on this, and in a later paper I was able to extend it to K dilates. It's worth mentioning that our techniques and Boris Buch's techniques are quite different. I think it would be fair to say that Boris Buch uses more general theorems from additive combinatorics, where our techniques are a bit more elementary. So many authors worked on lower bounds for the sum of dilates, with the question being, can you improve Boris Buch's bound to a constant? Most of the results were for P equals 1 and P equals 2, where Q either a prime or kind of close to a prime. Now if we go down to our main theorem, theorem 1.1, we can see that, for instance, taking P equal to 1, the bound is about Q to the Q squared. And you might ask, how close is this from the truth? On the next page, we show this nice construction due to Ruzha, which shows that you can't take the constant much better than square root Q to the log Q. The idea is to map a high-dimensional set to the integers, where the set in question behaves nicely with respect to dilation by Q. This construction only works when the size of A is small, and if the size of A is large with respect to Q, we expect the constant to be about Q squared. Okay, so let me just give some kind of higher level ideas into what's going on behind the proof. The main inequality we use is from equation 2, which is basically a trivial lower bound for the sum of 2 sets. Okay, so section 3 is when we start the proof in earnest. We have a bunch of important but kind of technical reductions that we do on the first page that I'll kind of just skip over right now. Equation 6 is pretty important and actually proves the result in a special case when A intersects every residue class modulo PQ. It's funny because if you're first thinking about this problem and you try this argument, you might actually think you prove the entire result. But it turns out that that's not the case. So a bit of a funny story. When Antal first showed the problem to me, he showed me equation 6. But he didn't really show me exactly equation 6. He replaced the R and the S with a P and a Q and ran the argument through, which would basically prove our final result with a much better constant. And I looked at him kind of strange, like wondering what was going on. And so I had to think about what the error in the proof was. And basically what can happen is the set A might not intersect every residue class mod PQ. And that's a significant problem which we have to work pretty hard to get around. But it's worth noting that if A does intersect every residue class mod PQ, which is basically what happens for a generic set, then equation 6 gives us the result we want to prove. So here's lemma 3.1, which is a crucial lemma in our argument. So if we look at kind of the form of the lemma, it says either Qj prime is FD, which means fully distributed, modulo Q. That means Q sub j prime would intersect every residue class, mod Q. And we know from equation 6 that that's good for us. And it turns out that Qj prime is closely related to Qj, enough that it implies a lower bound for the original problem we had in mind. So in the other case, we have this inequality, which basically means we get a small increment of this min of Q, the size of Q sub m. Notice on the left-hand side, we have an asymmetric sum of dilates, while on the right-hand side, it's symmetric. That is, both the dilates are the same set. It turns out that the right-hand side is nicer for ours because we can apply an induction argument, whereas the left-hand side kind of comes out naturally. This inequality is trivial if we forget that minimum of Qm, But with that extra minimum, that gives us just enough to do an inductive argument to prove what we wanted to prove. So here's lemma 3.2, which is in a similar spirit to the previous lemma, and is actually not even needed in the case p equals 1. So through a first reading, you could just take the case p equals 1 and ignore this lemma. And finally we have proposition 3.3, which immediately implies our main theorem. So we set it up where we have this quantity m, which allows us to perform an inductive argument. Actually, it turns out that we're inducting on this quantity m, which increases by 1 in each step. But in reality, if you look at the shape of the theorem, we're increasing the multiplicative constant by 1 over p plus q in each step. That was actually a crucial idea for us. That is, we weren't so greedy as to try to increase the multiplicative constant by 1 each time, but instead we just tried to do it by size 1 over p plus q in each step. This allowed us to really utilize lemma 3.1 in a pretty optimal way. You have to start off the induction somehow, and honestly you could just start off the induction by saying the size of p dot a plus q dot a is at least the size of a, and that would get things going. We do it in a little bit more fancy way to maybe get a slightly better constant. So for the rest of this, let's just assume that p is equal to 1. So basically what we do is break up A into residue classes modulo q. So we break up A into at most q sets such that all of the elements in a single set are the same modulo q. So this is exactly what the p sub i's and the q sub i's are. It turns out if one of the q sub i's is small, we can just use the trivial bound and induction to get a slight increment in the multiplicative constant. So we can assume all of the q sub i's are big. If all of the q sub i's are big, then we can apply lemma 3.1, and we can see on the right hand side that if all the q sub i's are big, then the right hand side will get a big increment. And that's basically what we do here. We break A into two disjoint sets and then use lemma 3.1 on one of the sets and induction on the other. If we are not in a position to apply that part of lemma 3.1, it turns out that a lot of these qj's are basically fully distributed mod q, and we can apply the original argument of equation 6 to get a lower bound. Actually, I lied a little bit. It's not the qj's that are fully distributed, but it's a translate and a dilate of the qj's that are fully distributed modulo q. And that's just a quick overview of the argument. If you have any questions, feel free to take a look at the paper or send me an email and I'd be happy to respond. Now you might ask, what are some future questions that are worth thinking about? So here's the first question, question 1.2, which is actually on Boris Buch's website, and he was the first person to show me this problem. So the question might look a little scary at first, so let me try to simplify it a bit. So the simplest case that I don't know how to solve would be A plus LA, where A is a subset of the two-dimensional integer lattice. So basically, A is a subset of an integer grid in two-dimensional space. And now you take A plus LA, and you can take L to be rotation by pi over 4. So basically, you just take A, and then you take the Minkowski sum of it with its rotation by pi over 4. Now, the conjecture is that set is at least 4 times the size of A minus little o of A. And I currently have no idea how to prove that. The question is a nice mix of additive combinatorics and geometry. Indeed, the analogous question for sums of convex sets in R2 comes down to the Brane-Minkowski inequality, which has a very geometric flavor. The point is it's not true if L is the identity, but as soon as you add this extra geometric twist into the equation, it turns out that it forces, as far as we think, it forces the size of the set with a dilate of itself to be large. So far, there hasn't been much done towards this problem. The next question I have is concerning A plus pi A, where A is a subset of real numbers and pi is a transcendental number. It turns out in this case, A plus pi A has superlinear in growth, as was shown by Konyagan and Laba. The main question is, what is the best lower bound one can find for this set? Finally, I'll mention one last result of Antal and myself. A year after our original sum of dilates paper, we thought about the analogous question for sum of dilates in vector spaces. We were able to show some initial results in this paper, but they're by no means optimal. Basically, we were able to show an optimal result in 2 and 3 dimensions and when q is equal to 2. It would definitely be interesting to extend these results to higher dimensions. What you run into is some higher dimensional geometry that we weren't able to tackle at the time. So the question I had in mind was conjecture 1.6. Here I assume A is a d-dimensional set. That's a subset of z to the d, and it's not contained in any hyperplane. So we conjecture in this case that A plus QA is at least, and we give a lower bound of q, the plus 2d minus 1 times the size of A, minus an error term. Now, the intuition from this is we think the minimizing example should basically be points in a line union with as few points as you can to make it a d-dimensional set. So basically it's a d-dimensional simplex together with a bunch of points that line a line. So the only progress towards this conjecture was what we made in this paper, where we basically replaced the 2d with a d, which is not as good. That's all I have to say about sum of dilates for now. Anyways, thanks for watching.